The constituent particles are closely packed in the crystal structure of solids. The close packing of constituent particles leaves minimum vacant space in the solids. By considering the constituent particles as identical hard spheres, now let us build the 3D structure of solids. Why to build the 3D structure? Because all real structures are three-dimensional structures, and it is important for us to understand the 3D structure. We shall understand the building of 3D structure in 3 steps. As first step, we shall arrange these spheres in a one-dimensional close-packed structures. This arrangement can be done in only one way. What is this arrangement? Yes, it is to arrange them in a row such that the spheres are touching each other. In this arrangement, each sphere is in contact with 2 of its neighbors. So, the coordination number is 2 in one-dimensional close-packed arrangement. Wondering what is this coordination number? It is the number of nearest neighbors of a particle. In one-dimensional arrangement, since each sphere is in contact with 2 of its neighbors, the coordination number is 2 in one-dimensional close packing. Now, if we place the rows of close packed spheres one above the other, we can generate a 2-dimensional close packed structure. Well, this can be done in 2 different ways. How you can arrange the rows of close packed spheres? Can you think of the arrangement? Okay, let us see. One way is to place the second row in contact with the first row in such a way that the spheres of second row are exactly above the spheres of the first row. The spheres of the 2 rows are aligned horizontally as well as vertically. If we call the first row as A type of row, then the second row is exactly same as the first row, which is also A type. Similarly, we can place more rows one above the other. So, we obtain A type of arrangement, as you can see here. You can see that in this arrangement, each sphere is in contact with 4 of its neighbors. So, what is the coordination number in this case? Yes, you are right. The coordination number is 4 in 2-dimensional close packing. Now, if the centers of these 4 neighboring spheres are joined, a square is formed. Hence, we call this packing as a square close packing in 2 dimensions. What is the other way that you can arrange these spheres? The second way is that second row may be placed above the first row in a staggered manner. Means, how do you place it? The arrangement is in such a way that its sphere fit in the depressions of the first row. So, how we are going to arrange the second row? In such a way that the spheres of second row fits exactly the depressions of the first row. In this arrangement of spheres, the first row, if we call it as A type, then the second row is different than that of the first row, so we can call it as B type. When we place third row adjacent to the second in the staggered manner again, the spheres are aligned horizontally and vertically with those of the first layer. So, this layer means the third layer is also same as that of the first row, that is A type. The spheres of similarly placed fourth row will be aligned with that of the second row, which is of B type. Fifth row is similar to that of the first row, A type, and similarly sixth row is same as that of the B type. Hence, the arrangement here is A, B type. Each sphere is in contact with 6 of its neighbors, and the two-dimensional coordination number here is 6 because each sphere is in contact with 6 neighboring spheres. If I join the center of 6 spheres, then they forms the corner of a hexagon. Therefore, this packing is called as two-dimensional hexagonal close packing. The hexagonal close packing is more efficient than square close packing. It is because in the hexagonal close packing arrangement there is less free space between the spheres. From the figure you can observe that in between the layers there are some empty spaces. These empty spaces are called as voids, and these voids are triangular in shape as you can visualize. Of course, you can see two different types of triangles that is present. In one row, you can see that the apex of the triangles are pointing upwards, and in the immediate next layer, you see that the apex of the triangles are pointing downwards. Let us move to see the last step towards the development of 3D structure of solids. The three-dimensional structure can be obtained by stacking two-dimensional layers one above the other. Just now we have discussed close packing in 2 dimensions. It can be of 2 types. What are these types? Absolutely. The square close packed structure and hexagonal close packed structure. Now let us see what types of 3D close packing can be obtained from these 2 types of 2-dimensional close packing. We can obtain 3-dimensional close packing from a 2-dimensional square close packed layers. The second square close packed layer is placed over the first layer such that the spheres of upper layer are exactly above those of the first layer. In this arrangement of spheres, both the layers are perfectly aligned horizontally as well as vertically. In the same way, we can place more layers one above the other. If the arrangement of spheres in the first layer is called as A type, all the layers have same arrangement. So, thus this particular lattice is called as A type pattern. The lattice so generated is a simple cubic lattice, and its unit cell is primitive cubic unit cell. The 3-dimensional close packed structure can be generated from 2-dimensional hexagonal close packed layers by placing these layers one over the other. Let us take 2-dimensional hexagonal close packed layers and place them one above the other, such that the spheres of second layer are placed in the depressions of the first layer. Let us call the first layer as A type, and since we have placed the second layer such that the spheres fall at the depression of the first layer, the spheres of the 2 layers are aligned differently. So, now let us call the second layer as B type. From the diagram here, you can see the arrangement of 2 layers. The bottom layer, that is A, is represented by dark red circles, and the top layer, that is the layer B, is represented by light red colored circles. From the figure, clearly you can observe that all the triangular voids of the first layer are not covered by the spheres of the second layer. Wherever a sphere of the second layer above the void of the first layer, or vice versa, a tetrahedral void is formed. Why the name is tetrahedral? It is because a tetrahedron is formed if we join the centers of the four spheres. And these tetrahedral voids are represented by the capital letter T in the diagram. Now here from these diagrams you can see the top view of the tetrahedral void as well as the exploded side view and the geometrical shape of the tetrahedral void for getting a better understanding of the tetrahedral void. At the other places, the triangular voids in the second layer are exactly above the triangular voids in the first layer. And these triangular shapes of these do not overlap. One of them has apex of the triangle pointing in the upward direction, whereas the other triangular voids have the apex of the triangle pointing downwards. And these voids are surrounded by 6 spheres. And so, these voids are known as octahedral voids. Here from these figures, you can see the top view of the octahedral void, the exploded side view of the octahedral void, and the geometrical shape of the octahedral void for getting a better understanding of the octahedral voids. From this diagram, clearly you can see all the tetrahedral voids which are represented by the capital letter English alphabet T, as well as the octahedral voids that are marked as capital letter O. Now, if we want to know how many voids are present in the crystal structure or how much voids are there in the given structure, to answer this particular question, this answer depends upon the number of close packed spheres. If I consider the number of close packed spheres as capital letter English alphabet N, then the number of octahedral voids generated in the crystal is also equal to N. That is, the number of octahedral voids is equal to the number of close packed spheres. And the number of tetrahedral voids generated is equal to 2n. Means the number of tetrahedral voids is twice that of the number of close packed spheres in the crystal. How we can place a third layer over the second layer now? There are two possibilities by which we can place a third layer. One way is by covering the tetrahedral voids, and the second method is by covering the octahedral voids. How we can cover tetrahedral voids? Tetrahedral voids of the second layer are covered by the spheres of the third layer. If the sphere of the third layer are exactly aligned with those of the first layer. So, if the first layer is A type, then the third layer is also of A type, whereas the second layer is B type. And this pattern of spheres is repeated in every alternate layers. This pattern often is written as AB pattern. This structure is called as hexagonal close packed structure. In short, it is written as HCP structure. Metals like magnesium and zinc possess this type of arrangement of atoms. Instead of this, if the third layer is placed above the second layer in such a way that its spheres covers the octahedral voids, the alignment of spheres of third layer is different than that of the first as well as second layer. So this arrangement is called as C type. Only when the fourth layer is placed, its spheres are aligned with those of the first layer. So this pattern of layers is represented as ABC. This structure is called as cubic close packed structure, or it is also called as face centered cubic structures. In short, the structure is called as CCP or FCC structure. Metals such as copper and silver crystallizes into CCP or FCC structure. Both these types of close packing, that is the cubic close packed structure and face centered cubic structure, are highly efficient and 74% of the total space in the crystal is filled. Here, each sphere is in contact with 12 spheres. So, the coordination number is 12 in either of the two structures.